Okay, welcome back. In the last video, we learned how to complete the square and a way to obtain a vertex form for a function. Now we're going to look at a partial factoring method. So this method actually doesn't put our function into vertex form, but it helps us find the vertex. And it's actually a very clever way of doing so. These are our steps. We're going to take our quadratic and we're going to drop the constant term. Okay, that poor little constant term is always being left out. So we're going to drop it and then common factor the remaining two terms that are in the, I'm going to call it the new equation. Okay, from this new equation, we're going to determine its zeros. Okay, I'm not sure if you're familiar with the term zeros, but zeros are another way of basically identifying the x-intercepts. Okay, so when we get the x-intercepts for this new equation, we can actually find its axis of symmetry. Okay, to do the axis of symmetry, we're going to take those two x-intercepts, and we're going to add them together and divide by 2. Okay, so the x-intercepts that we found in part C, we're going to get the average value. This is going to be our axis of symmetry for the quadratic. We know the vertex is always placed along the axis of symmetry. So once we get that x value for the vertex, we go back to our original equation, sub in that value of x, and then solve for y, and that would be the y value of the vertex. Okay, so let's just go ahead and do an example. So find the vertex for this function by partial factoring, and then state if it's a max or minimum. Okay, so our first step is to take our quadratic and drop the last term. Remember that constant term? Okay, we got to get rid of it. This is now a new equation that we're looking at. Okay, and so this new equation, I'm just going to call it y equals. All right, and our next step, we got a common factor the remaining terms in the new equation. So I want to take out the greatest common factor. So I'm looking at the biggest coefficient I can take out and the biggest value for x. Okay, so as you may have guessed, we can take out a 4 and we can take out an x. Okay, when I factor it, I'm dividing it out. So if I divide this by 4x, the 4 will be gone and one of the x's will be gone, and I'm left with just an x. Okay, if you're not sure if you're doing this right, you can always double check. If you multiply this back in, you should get this right here. Okay, all right, now for the next term, divide this by 4x. Okay, so negative 12 divided by 4, that's just negative 3. And x divided by x, well, that's just going to get rid of the x value. So I'm left with just that there. Okay, so again, just one more time, if you want to check, you could distribute this in, and you should get the same thing up here. Okay, step C, it says determine the zeros are the x-intercepts. So if I want to know the x-intercepts, remember that zero property theorem? Okay, the zero property theorem states that if you multiply two things and it equals 0, well, that's only going to happen if either of these are 0. So either A is 0 and or B is 0. Okay. Well, my x-intercepts are going to be the values of x that make this 0 or this 0. Okay, so what would I need for this first bracket to be 0? What would x need to be? Well, it's pretty obvious. If I want to make that whole term 0, x should just be 0. What would make this next whole term 0? Well, x should just be 3. Okay, these are called the zeros or x-intercepts. Okay, and on the graph, I could actually draw those x-intercepts now for this equation. I would have an x-intercept at 0. My other one would be at 3. Okay, so this is really handy to know because I know now that there's an axis of symmetry between those 2 points. Okay, so my axis of symmetry, if I wanted to calculate it, well, it says here we can just add those two zeros. So R and S, those are the zeros, or the x-intercepts. I can add them together and divide by 2. So basically find the average or the middle of them. So remember, the axis of symmetry is always situated smack in the middle between the two intercepts. So This distance here is the same distance there. They're equidistant, so this is the average. So let's just add them up and then divide by 2. We get 1.5. Okay, so I now know the axis of symmetry is at x equal to 1.5. Okay, so like I kind of sort of mentioned before, what does this have to do, this axis of symmetry, what does this have to do with our function? Okay, because notice we changed it. We got rid of that 3 at the end. Well, we should know from math classes previously that whenever you add something to the end of a function, like a plus 3, all it does is move everything up 3 units. So these two functions are very similar. The only difference is this one is 3 units higher. So that means my vertex for this is actually just 3 units higher than the vertex for this. Okay, so that's kind of why we drop that constant term. If I try to factor this, it could be a little bit difficult. So what we do is we drop it and we factor something similar. Okay, and we get that axis of symmetry. So the axis of symmetry for this equation is the same as the axis of symmetry for this equation. Okay, let me go ahead and show you this on Desmos. Let's type in the original function first. And it's plus 3. Okay, and we'll zoom out a bit. Okay, notice here the 0 for this is not, the x-intercept is not 0. Okay, that's because we found the zeros for the second one. Okay, let's plug in the second one. It's just 4x squared minus 12x. Okay, gotta get that 12 back in there. Okay, there we go. So those are the two equations I'm looking at. And let's zoom in. Oh, I must have an error somewhere. I'm missing my exponent there. Let's put that back in. There we go. Much better. Okay, so those are the two quadratics. Okay, so you can see how they're basically almost identical. It's just that this one and this one, there's a difference of 3 in their vertex. Okay, so by adding that plus 3, the whole graph just bumps up 3 units. So this is a very clever way of getting the vertex by making our function a little bit simpler and then factoring it, getting the zeros, and then finding the axis of symmetry. Okay, so we're not done. We just have to take this axis of symmetry and we got to plug it into the original function. Okay, so we're now going to find f of 1.5. Okay, so I know my vertex is somewhere along here at 1.5. Okay, I just don't know the y value. So if I want to get the y value, well, that's really easy. We're just going to plug the x in for all our values of x. So that's what I'm saying to do here. Okay, 1.5 squared. That's not really a nice number. What I'm going to do is I'm going to put this in a fraction form, 3 over 2. That's what 1.5 is, 3 over 2. And that'll hopefully help me to get a whole number. That way I can avoid using the calculator. This is still squared too, by the way. Don't forget to square. Okay, so we're going to have, when we square a fraction, we have to square the top number and the bottom number, the denominator. Okay, so 3 squared is 9, 2 squared is 4. Okay, this one over here, well, I can clean this up a bit. 12 over 2, that actually simplifies to just 6. So I got minus 6 times 3, that's minus 18. And then we have plus 3 at the end. Okay, this worked out really nice because you can see here, even the 4's cancel out. 4 times 9 divided by 4, the 4's cancel. So we just have 9 minus 18 plus 3. and that works out to -6. So I now just found the y value for the vertex, this missing value here. So we can say, therefore, vertex is at 1.5 comma -6. Okay. You could also write 3/2 here. That would be fine as well. Okay, let's go back to the top here. A is 4, so this opens up. Therefore, we have a minimum. So since A is greater than 0, this opens up. Okay, therefore 1.5 comma -6 is a minimum point. And that is how we can use partial factoring to get the vertex and find if it's a maximum or a minimum value. Okay, in the next video, we will just be solving some application questions.